Hello. Welcome everybody to the MIDAS seminar series. This is our very first seminar of the 21-22 academic year. We're in this semi-pandemic driven mode, which means that many of our seminars, including this one today, are virtual. And that's how it's going to be, at least for the next few weeks. And then we're hoping that things will be better. Always looking for a better tomorrow. So I'm delighted that we're able to open our seminar series this year with Professor Olga Russakovsky from Princeton University. She's a professor of computer science and was one of the creators of ImageNet, which, if you've not heard of, is the standard collection of images that is been used for a broad range of image recognition work over the past several years. And Olga is going to tell us more about that, I'm sure, because her talk is about fairness in visual recognition. The data sets that she's talking about redesigning presumably have to do with ImageNet as the original ImageNet as the starting point. And I'm really excited to hear what she has to say. But before she starts, I'd like to thank our sponsors, Quicken Loans, the American Mathematical Society, Microsoft, General Dynamics, Yazaki. And we have a really exciting lineup of speakers the rest of the year. Specifically, the next 3 weeks, we have Greg Asner from Arizona State next week, talking about data science and coral reef protection. We have Stefano Arman from Stanford University on September 27th, talking about artificial intelligence for sustainable development. And then on October 4th, we have a double header with Ji Chen and Linwei Hu, both giving their perspectives on explainable machine learning. So I hope to see you all at these talks. And with that, I'd like to turn this over to Olga. Thank you for being here. Look forward to your talk.
Awesome. Thank you so much. Huge apologies to everybody for being a little bit late. That was entirely my fault. That was my computer's fault, if we're being honest, in Zoom land. So I hope I hope you all understand and are familiar with these current challenges. So let me share my slides here. So I'm going to assume that everyone can see my slides. But yes. You know, no, yes, excellent. Thank you, James. So thanks very much for having me. So I do, in fact, want to talk about fairness in visual recognition. I was kind of on the fence about whether to talk about some of our ImageNet work here or not, but I'm very glad that I actually did, in fact, add those couple of slides back in here. So we'll definitely cover some of that work. I don't know. I guess we'll do all the questions at the end since it's a webinar. Does that seem right?
Yeah, that's just
okay.
right.
Okay, great. All right, so let's dive in. So fairness in visual recognition. So a number of years ago, as computer vision sort of started being actually practically useful and being deployed in practical settings, there have then correspondingly been a number of sort of an increasing number of issues that have been sort of revealed and brought to the public's attention, brought to the scientific community's attention. And these are things like computer vision model that quote unquote learns to increase attractiveness by manipulating skin color, or machines that are taught by photos that learn a sexist view of women, or facial recognition is accurate, but only for white men. And so there is a lot of very deep questions about like, what is the impact of this this kind of behavior of the model? It's kind of what are the root causes? And there's this great book. I mean, there's many books, but there's one in particular that I really like called Race After Technology by my colleague at Princeton, Professor Ruha Benjamin, that really dives into the really provides a very rich view of this kind of technological artifacts, technological behavior. But for the purposes of this talk, right, so I'm actually not an expert on critical race theory, not an expert on science and technology. I am or an expert in science and technology, not an expert on technology and society. So I will simplify this down for the purposes of this talk and just say, okay, there's some kind of cycle that happens where human history, bias, and prejudice is making its way into large scale data, which is then making its way into AI models and making its way into AI decision making. And then that now becomes, as we deploy these systems in high stakes scenarios, this becomes part of our history, part of our world. And so the question that I want to ask from the technical perspective, from the AI perspective, is can we adjust the AI design to try to mitigate some of these effects in this cycle? And so this is the kind of work that we've been doing over the past few years in my lab, and we'll kind of dive into the different pieces here. We won't spend too much time on any one particular paper, but we'll sort of give you a sense of the overall research agenda here. So let's start, in fact, by talking through the large-scale data piece. So there's been a number of works in recent years looking at kind of what does large-scale data look like for computer vision, for AI generally, and kind of the key takeaways that just because the data is large-scale does not mean that there's fair representation within the data. It does not mean that everybody is fairly, appropriately, accurately represented in this data. So there's a number of works. So for example, the seminal work by Joy Buolamwini and Tamir Gebru in 2018 that points out that there is a lack of race diversity in face data sets. So the face data sets that are being used are predominantly people with lighter skin. There's been sort of a number of other works around kind of demographics of people in the data sets. In 2017 and several papers since then have pointed out that in addition to sort of demographic, or maybe underlying the lack of demographic diversity, there's also a lack of geographic diversity. So if you look at data sets like ImageNet or like Open Images, sort of popular computer vision data sets, and you plot on the map of the world kind of where they come from, it turns out that they predominantly come from the US or Europe, and then there's like entire continents like Africa that are not represented in this in these data sets. And so what does that mean? It's not just the misrepresentation of people of certain demographics. It's also, even if you look at something seemingly innocuous like object recognition, it turns out, so this is the paper from 2019, turns out that even for object recognition, current models are learning to recognize objects as they common household objects as they appear in the US. And so one example that they gave is that models trained from modern computer vision data sets will recognize liquid US brands of liquid soap and then fail to recognize bar soap, even though sort of soap primarily in the vast majority of the world, it comes in the form of bar soap, right? It doesn't come in the form of liquid soap. But because these data sets are so US centric, that's what is in the data. And even for something, again, like, let's recognize common household objects, this has nothing to do with people, nothing to do with demographics, arguably, right? It still has this kind of geographic bias in it. And a lot of these effects can be traced back, not all, but a lot can be traced back to the lack of diversity in image search engines. So the fact that all of this data, kind of the cheapest source of visual data and the most easily available source of visual data is through the web, through the photos that are shared online on social media and so forth. And most of these data sets that are used in computer vision are constructed by querying the web for particular concepts that we want to represent. And there is, a number of papers and a number of books, such as Algorithms of Oppression by Sophia Noble, written about kind of what do search engines actually bring to the surface. So for example, if you Google the term CEO, right, you're going to get a lot of photos of primarily white men in suits. And so that gives you, a very particular view into what that concept really corresponds to visually. So one of our first kind of lines of exploration into this space has been looking specifically at the ImageNet data set and doing analysis on this one particular data set. So I'll talk a little bit through that, and then we'll kind of generalize this to a tool that's more broadly applicable to computer vision data sets in general. So the first line of analysis, right, looking specifically at ImageNet. So ImageNet is a data set, if you haven't heard of it, with 20,000 visual categories, and the categories are organized into a hierarchy based on WordNet, which is a linguistic ontology of concepts in the English language. And these 20,000 categories are illustrated with 14 million images. This was a paper published by my colleague Jia Deng in 2009. Well, Jia Deng and others, of course. And on the right, you can see, so for various visual concepts like hammer, cup, or runner, or banana, right? So each of those would correspond to a node in this hierarchy. And they're illustrated by photos collected from the web in a semi-automatic fashion. You kind of query for these objects on search engines, and then use crowdsourcing, use people to sort of clean up this data and make sure there's no errors, or there's limited numbers of errors here. So why are we focusing on this data set in particular? So it's the standard benchmark for visual recognition, and it's become, extreme. I'm not going to talk through all of the impact of ImageNet, but it's become kind of the de facto gold standard benchmark for developing new models for visual recognition. And then it's also used for transfer learning to a wide range of applications. So a lot of kind of visual applications that you might end up using, the way that they're being designed is actually you sort of develop a model and pre-train the model's parameters on ImageNet, and then you use that as a backbone to do various different applications. So this is part of why you kind of, it makes a lot of sense to dive deep into this particular data set and kind of see what's hiding in here. And again, the thing to remember is that we're talking in the order of 14 million images, right? So it's not going to be possible for us as researchers to look through it and kind of look at every particular image in there, but we can try to at least get a sense of like, okay, what might be going on in this data set. So there's two works. Again, I'm not going to sort of talk in great depth about any of them, but I do want to mention them around, specifically digging deeply into ImageNet. So the first one was from 2020. So it was published in the Fairness, Accountability, and Transparency Conference. So it's called Tourist Fairer Datasets, Filtering and Balancing the Distribution of the People Subtree in the ImageNet Hierarchy. And so in this work, we specifically, so I mentioned the category hierarchy is organized according to WordNet. So we looked specifically at the person subtree of this hierarchy, and we said, okay, there's a bunch of nouns in WordNet that correspond to kind of different people. So some examples are here on the slide. So it's like conversational partner or groom. And so we looked at like what kinds of images are actually illustrating these concepts. And we've done a number of, sort of both qualitative and quantitative analysis, also looked at demographics of the people that are represented there, and made, some number of findings, made some cleanup to the data set, sort of removed some categories that were in there that kind of made sense maybe in the context of WordNet, but then did not make any sense in the context of being able to actually illustrate that they were non-imageable categories. So it didn't make sense to illustrate them with images. Also, found a number of categories that really shouldn't have been there in the first place, that kind of appeared in WordNet, but had a number of racial slurs, for example, quite unfortunately, that we got rid of, and again, shouldn't have been there in the first place. And so really kind of did a more sort of fine-grained analysis of this particular subtree in the data set. But then the part of the reality of ImageNet is that it is again, so it's a data set with really 14 million images and 20,000 categories, but typically when you hear ImageNet, what people are actually referring to is 1,000 categories of those 20,000 and about 1.2 million images, because that's the ImageNet challenge. So that's actually a subset of ImageNet of particular categories, and actually by and large, not people categories. So they're by and large sort of common object categories. And that's what is used as the benchmark for visual recognition. That's the subset that's primarily used when you're doing transfer learning. And so we next kind of turned our attention specifically to these categories that are most commonly used in the ImageNet challenge. Again, so the 1,000 categories that you likely have heard about. And so so out of those, only 3 are people categories and the rest are objects. So one of the things that we discovered there, and this has been, this is sort of not a shock, is there's a lot of spurious people that appear in these photos, even though the categories that are trying to that we're trying to illustrate with images are not people categories. So some examples here on the right are like things like barber chair or husky or beer bottle, right? These are objects. However, when you search for these terms on Google or on various search engines that we pulled photos from, you end up getting kind of people in these photos. So our question that we wanted to ask is, right, so this is potentially a problem. So these are people who, may not have consented to being in this data set. And even though, I mean, we can, again, I'm not a legal expert, so we can talk about, there's a particular legal agreement around ImageNet. There's a particular, legal license for using this data set for academic purposes. But there's also the question of like, right, can we do something about the fact that there's all these people in the images? And part of what we did is we went ahead and annotated and removed all of the faces. So here I'm showing sort of the faces blurred as a result of our interventions. Actually, we can both blur and just sort of overlay a gray box on these photos. And what we wanted to show is sort of 2 things as a result of it. One is that visual recognition accuracy, so sort of the benchmark for visual recognition for recognizing these 1,000 categories is essentially unaffected when you do this, right? So all of the kind of all of the findings, all of the what are people actually using this for is for developing better visual recognition technology. So all of that still works quite well, even when you sort of obfuscate faces in this way. And more importantly, sort of transfer learning ability. So the kind of features that you learn from this data set, transfer learning ability is essentially entirely unaffected by this. And so this is, a very particular intervention that we do in a particular data set where we say, okay, this is a problem. Let's obfuscate these faces. Let's retrain some of these models, and let's release this, a better, cleaner version of ImageNet to the community. So, of course, this line of work, so while very, very important to do, particularly given the impact of ImageNet, at the end of the day, this is pretty specific to one particular data set. And so the kind of analysis we do here is quite specific to this exact use case. And so what we where we went from here is thinking about, can we develop a tool for actually measuring and mitigating bias in visual data sets generally? And so here we are not looking at privacy. What we're looking at is sort of bias of the form, particular demographics of people, how they are represented, how they appear in modern data sets. And so this is meant to be a general tool that takes as an input a visual data set of the kinds of which there are many. I mean, there's ImageNet, but there's many, many others, and reveals potential social biases here. So, so actually for many of the works that I'll talk about from here on out, I'll kind of do this like one spotlight slide per paper, just to make sure we're kind of, we can get through a lot of papers, but I'm able to kind of show the key contributions and the key summaries here for you. So we kind of have a structure here going forward. So the contributions of this work, right, is we're trying to aid dataset creators and users by revealing biases in large-scale visual data. So for us, right, so we can, spend a lot of time looking at ImageNet because this is part of the, this is the data set that we had built. So it's, we have a responsibility to do this deep dive. But in general, right, we want to make sure that this is, this kind of analysis and deep dive is easier for researchers going forward, both for data set creators as well as for users of these data sets. And so this tool sort of revised, it leverages the available annotations, so any kind of visual annotations you have on the data, any existing vision models, census data, sort of whatever you have access to about this data to then identify bias in representation of people of, representation of objects, of people of different demographics and of geographic regions, and then suggest actionable insights to the user. So let me give you one concrete example. So here the images are images from the COCO dataset that you may or may not be familiar with, but essentially these are images from Flickr of common household scenes or common everyday scenes, not necessarily household, it's sort of common, essentially photos from Flickr illustrating some common objects, common environments. The annotations that we're using, one is inferred gender of the people in the images, and so this is based on prior work. And two is predicted scene labels, so the kinds of scenes that are depicted in these images, and this is predicted. So if we had these manual annotations, we could use those. But if not, then we're using sort of predicted scene labels, and this is trained using the Places network. So it's basically a deep learning model that runs on these images and says, okay, here's what scene I think this corresponds to. So in the graph, the graph is an example of what the tool would return. So on the y-axis, you see the different kinds of scene labels. So this is 16 different types of scenes. So like this may be a mountain scene, this may be a water, ice, snow scene, an industrial and construction scene, and so on. On the x-axis, you see the fraction of images with the scene, and they're broken up by whether the image whether the people depicted in these images are inferred to be male or female. So I will absolutely do the caveat here, right? So we're assuming a binarized gender. We're also using inferred gender, right? So this is not self-reported. So these labels are definitely, there are some errors on the individual level, but hopefully on the whole, this gives some reasonable statistics about the data, even though, of course, this is definitely imperfect assumptions. And so the kinds of things that you can see out of this analysis emerge, and this is where you kind of need sort of human intervention to look at this these statistics and decide, is this the kind of patterns that you want in your data or not? But you can see, for example, so outdoor sports and fields and parks in this data occur primarily with people who are likely to be male. The shopping and dining scenes occur primarily with people who are likely to be female. So, then for you, the question is, as a dataset user or as a dataset creator, are these the kind of patterns that you're okay with in this dataset, or would you like to go ahead and, collect more images of particular type to try to counteract some of these revealed statistics? Right, and so the example finding is within this COCO dataset, men and women are typically depicted with different objects and in different scenes. So this is sort of this brings me to kind of where we are right now with large scale data. There's a number of ongoing projects sort of thinking again from this perspective of what kind of constructive solutions can we develop to try to make sense of this large scale visual data, and what kind of intervention strategies we can design to try to counteract some of the perhaps undesirable effects in there. So I see a number of questions in the chat, although when I'm sharing slides, it's a little bit hard for me to actually see those questions, but this is a good time. Oh, never mind. Okay, they're not about their logistics.
No, I think they're all procedural. Just keep going.
Okay, excellent. Okay, then I'll keep going. All right. So all of these interventions on the data side, so they're all great and critically important, and we'll absolutely continue pushing on this direction. But one of the challenges here is that at the end of the day, so the data will at best, well, so the data will reflect some kinds of issues in the real world, right? So there's always sort of this tension between the fact that our world is inherently, well, not inherent, our world is in reality imperfect. There is bias and prejudices and stereotypes in the real world. So that makes its way into our large scale data. We can try to intervene, but sometimes it's actually not going to be possible to collect sort of perfect and ideal data. And so that's why we turn our attention to the models, right? So we think about, given imperfect data, can we try to train models that sort of do better than even what's reflected in the data, to do models that are able to learn from imperfect data, but then sort of do the right thing, quote unquote. And so there's many challenges in building fair models, right? So this is coming from, there's things like just learning with long tail distribution, learning with, and this is, goes beyond fairness. This is, a question in all kinds of settings and visual recognition with, so this is a paper from a long time ago on object detection. That's sort of, there will be a lot more examples of some concepts than others, and sort of are you able to train models well from it? There's related questions around interpretability. How do you make sure that the model is sort of doing the right thing, but also for the right reason? How do you understand what is the rationale, kind of what's the reasoning process in these models? And understanding pathways of bias propagation. So how does bias in the data, or any sort of whatever imperfections, whatever statistics are in the data, how does that propagate into the models? There's questions around quantifying fairness and lots of different metrics developed for measuring fairness. Also a great paper recently by Gail Jacobs and Hannah Wallach around, like, what are we even really quantifying here when we're talking about fairness, and when we're talking about applying machine learning to do all kinds of tasks in the world, like what are we really measuring? And then a lot of works, if you're kind of more interested in this space and studying sort of some of the history of machine learning fairness and how that all came about, there's kind of great works that provide an overview of that. But here I sort of, again, want to kind of dive into and give you a flavor of the kind of work that we've been doing and the kind of way that we as computer vision researchers have been thinking about some of these problems and have been sort of contributing our engineering knowledge to try to make headway in this space, and to try to make sure that these computer vision systems that we're actually building are better and less biased than they would be otherwise. And so the first paper I sort of want to highlight is called Understanding and Evaluating Racial Bias in Image Captioning. So this was just accepted to the International Conference on Computer Vision, to ICCV this year. And so the goal here is to understand why and whether racial biases exist in image captioning system. I think this has been, quite well established in the literature, but we are trying to a little bit better understand kind of where exactly in the process of training an image captioning system, where exactly in the process does bias come in. And so we sort of make kind of two key contributions here. So one is, I don't know if you remember what I talked about Revise a few minutes ago. I said we're using inferred gender labels from prior work on these images. So in fact, what we were using is gender labels derived from image captions. So it's actually like a very, very imperfect proxy for gender labeling. And that's what's been used in the literature for quite a while in this data set. So long story short, so we went ahead and annotated perceived skin color and perceived gender expression of people in this data set, which again, these annotations are not perfect for a variety of reasons, but at least we are sort of closer to the data and can make some analysis of whether these annotations are actually correct or not, or hopefully are sort of more correct than the ones that were automatically generated before. And so using those, we're trying to analyze pathways of bias propagation so the task of image captioning, right, is you have some photos, you have some people who've written captions of these photos, and then you are training a computer vision model to produce those, to sort of automatically caption these images. And so the kinds of things that we've analyzed, right? So in images, if you look at just the photos of people with lighter versus darker skin in this data set, so there's differences in visual appearances of these images sort of beyond the skin color of the people, like, no, ignoring that, so masking out the people. So there's some differences in visual appearances of those images, which might contribute to the differences in downstream automatic captions. There's also differences in how people who've provided this training data, people who've annotated these, what kind of language they used in describing these photos. And so we've identified a number of uses of racial descriptors and slurs in the manual captions that were provided as input to these computer vision systems. And then there's differences in caption sentiment and content. And finally, for the automatic captions, right? So we've noticed that there's some use of racial descriptions and offensive language, although not as much actually as in the manual captions. There's slight differences in accuracy between photos of between automatic captions on photos of people with lighter versus darker skin, and there's differences in caption content. And so one example finding here, and I'll kind of refer you to the paper if you want to learn more, is that even after controlling for visual appearance, so even sort of trying to find, so we did this by trying to find pairs of images that are as similar as possible, except for the skin color of the person. So even after controlling for visual appearances, the captions differ in word choices used to describe images with lighter versus darker skin individual. And what was particularly interesting to us, although these findings are not as strong as we would hope, so we're still sort of digging into this, but it appears that this is particularly apparent in the manual captions, so in the sort of human written captions, as well as in the newer transformer-based models. So one of the kind of interesting, so for those of you who are like familiar with computer vision with building image captioning systems, so a lot of the systems right now are not very accurate. So they describe sort of they describe the image at a very high level without focusing on the details. And so the sort of older computer vision models, there's not very much bias in them, basically because they sort of state obvious things about image. But part of what we're observing is that the trend towards the newer models that are actually becoming sort of more descriptive and are really kind of providing more detailed descriptions of the image. So those are the ones that are starting to exhibit some racial bias, which is kind of consistent with the general trend that as computer vision is becoming sort of more and more accurate, that's when a lot of these kinds of fairness questions are starting to appear. And so, right, so one of the questions here is, how do you actually measure fairness? So how do you measure sort of what is going on in these models? And in particular, right, so before talked about bias from the manual captions that are potentially making its way into the automatic captions. And so one of our also sort of recent questions, this was published at ICML of this year, is developing a new metric for measuring social bias amplification. So one of the, one of sort of the places where it is completely clear that intervention is needed, and in fact, it's very clear how you need to intervene, is places where these models take bias that's in the data and then further amplify it. And so this has been shown in a number of prior works that, right, and it's, it's a statistical fact, right? These models are statistical systems that are trying to learn to make accurate decisions for the majority cases. And so in doing that, they will frequently sort of overfit to the majority and will make decisions that are best in the majority for the majority, and in that way actually will frequently amplify the social bias that exists in the data. And so in this work, we kind of make two key contributions. So one is we're proposing a new way to measure the amount of bias in the models compared to the bias in data. And the second, we actually analyze this new metric in diverse applications. So let me just talk really briefly through this like massive equation on the left, because it's actually not as complicated as it looks. But basically we are trying to, so first we have a set of protected attributes. We have a set of target labels. So this is, for example, on, we're trying to predict, you know, objects that appear in images. So we're trying to do image classification. So that's our set of tasks T that we're trying to recognize. So for example, let's say T can be a computer. So we're trying to predict whether this photo contains a computer or not. And then A is a set of protected attributes. So let's again use binarized gender. So we're trying to predict T is 1 if we're sort of predicting that there's a computer in there. T is 0 if there's no computer in this photo. And then A is 1 if there is a woman in the image. A is 0 if there's a man in the image. So the metric averages over all pairs of these target labels and protected attributes. There is a binary variable corresponding to whether this attribute and this target label are positively or negatively correlated, right? So is the presence of computer positively correlated with the presence of a woman, or is it negatively correlated? So that's Y sub AT. And then there's a delta AT term, which if we just look at the top part of this, it essentially says, okay, what is the probability that we're going to predict that the computer is in the image, given that there is a woman in the image, minus the probability in our training data that there's a computer in the image, given that there is a woman in the image. So basically, how much is the model's prediction amplifying the amount of correlation in the data? And so this is if we're measuring the amount of bias that is the amount of influence that the presence of a woman in the image has on the computer, and vice versa if we're trying to measure the amount of bias amplification from sort of how much and then the bottom part of this equation is if we're trying to measure how much the presence of a computer is influencing our prediction of whether there's a woman in the image. So so now I can't possibly sort of do this work justice in a short period of time, but hopefully this kind of gives you a high level sense of like, okay, what are we actually trying to quantify? It's basically how much more likely our model is to make some kind of prediction in the image, and some kind of, in particular, sort of undesirable prediction compared to what is actually available in the data. And so one example of finding here, right, so I'm not going to dive through the different possible applications, that some prior strategies for mitigating bias amplification actually fail under the new metric. So there were a number of previous metrics that have been proposed, and so we kind of analyze those. And one of the things we discovered is that there is some, in the computer vision literature, there have been some strategies proposed for mitigating bias amplification, but actually when you kind of measure it properly using this new metric, it turns out that there is that there are artifacts due to things that have nothing to do with bias amplification. Artifacts and how it was measured led to some erroneous conclusions. All right, so the next two papers, and they're the last two papers that I'll sort of talk about, are much more technical, in specifically working with deep learning computer vision models for trying to directly intervene and mitigate biases. So mitigate bias amplification, mitigate bias propagation in these systems. So the first piece of work is on exploring techniques for training classifiers on data with spurious correlations. And so some of the contributions here are to propose a simple data set with controlled biases, analyze multiple bias mitigation techniques, and then validate on more realistic benchmarks. And so this is a more classical kind of machine learning computer vision paper where we just sort of go ahead and try a bunch of different interventions, a bunch of different algorithms, a bunch of different models. And so some of the kinds of findings that we're really, so this is now much more on the like actual interventions, is that, so you can do over and under sampling. So for example, right, if in your data set, you have a lot of women that appear with computers, but you have, you actually want computers to be uncorrelated with, so what computers to appear with equal frequency with men and women, you might want to sort of resample your data to try to counteract this effect. And so, of course, like over and under sampling is a viable strategy, but it's prone to overfitting and numerical instability, so it does not work very well in practice, particularly in very long tail settings. Adversarial debiasing is a strategy that has been proposed in the literature for essentially saying that I want my model for predicting whether there's a computer in the photo or not to be so I want the feature representation that's learned in this model to be unable to classify gender of the person in the image. So it's basically trying to intervene at the feature level and say, okay, I want my classifier for my target label, like computer, to be entirely independent from the classifier for gender, and in that way sort of make sure that the model does not have any kind of gender bias. So it turns out in practice, and this has been shown in a number of work since then as well, that adversarial debiasing does not work very well because it harms the classifier much more than it makes it unbiased, but it also really harms the accuracy of the classifier. And so finally, we propose a particular technique, which we call domain independent training, although it's a well-established method. The method itself is not super surprising, but it's basically training separate target classifiers, so separate object recognition classifiers for each protected attribute value. So training a separate object classifier on images with women and a separate object classifier on images with men, and then combining those tends to be surprisingly effective at mitigating sort of any kind of gender correlation with your target target labels that you're trying to predict. And finally, just very quickly, right? So there is kind of continuing on this work, we've developed a method for training visual classifiers on data with spurious correlations. And in this case, we actually are doing this with a new generative adversarial network-based, so GAN-based dataset augmentation strategy that removes correlations. And so the goal here, right, is you have some kind of imperfect data. So can you automatically generate better or less biased data? And we show that this works on Celeb-A, on a standard data set of recognizing face attributes. And long story short, so GANs are great, but very difficult to work with. And certainly this is very difficult. This is a very difficult approach to get to work in a more realistic setting than just faces. So generating faces is sort of easier, but as you move to more complex scenes, this becomes harder. But we demonstrate improvement in fairness over prior art and also do some analysis of this particular benchmark. And so we demonstrate that we're able to do to train models that are more fair according to a number of fairness metrics. So but slightly worse in terms of accuracy. So AP here is accuracy, and then DEO, BA, which is bias amplification, and KL divergence between the score distribution on the two protected attributes. So all of those are better with this GAN method. And kind of the key finding here is that a single GAN is sufficient to do the augmentation. So some of the prior work has shown that you need various generative models to do this, but it turns out just a single one is sufficient. So let's sort of pause the technical bit here, because I first of all want to leave time for discussion, and second of all want to say one more bit here besides the data and the models. But I hope that this, so I know I'm sort of deliberately not going into particular depth on any one piece of work. I hope this gives you a sense of the kind of pieces that we're able to sort of bite off of this very, very large and complex problem. So this is, it is extremely difficult to make headway in this space because it's a very, very rich, very complex space. And what we're trying to do is sort of simplify this down into kind of bite-sized chunks, and in particular, bite-sized chunks that somebody with sort of our expertise of computer vision, machine learning engineers can start sort of breaking off this very complex problem and start kind of making some small headway towards mitigating some of the bias, mitigating some of the kind of problematic behavior that these systems are exhibiting. And so the last thing that I do want to talk about here, right, is that as we're doing this, so one thing that's going to be extremely influential and extremely fundamental to trying to mitigate some of these bias and these effects is going to be thinking about who are the actual decision makers who are going to be deploying these systems, who are the people who are developing these systems, right? So we're coming at it in my lab from a particular perspective, right? We have particular backgrounds, particular expertise, particular viewpoints, right? But thinking more generally about the AI field, so who is doing work in this space? Who is building the models? Who's doing work on mitigating bias? Like who is making decisions about where they're deployed? Who is making decisions about where the data is collected? Like who is asking the research questions? And, I hope I'm preaching to the choir when I say that, the AI field is extremely homogeneous right now. So we have dramatic lack of diversity among the people who are impacting this technology. In particular, as we move higher up in the pipeline, we have less and less diversity. And so a few years ago, Fei Li, who I hope many of you have heard of, so she's a professor at Stanford, Rick Summer, who is an expert in K-12 education, and I co-founded AI for All, which is a nonprofit dedicated to increasing diversity and inclusion in AI. So we view this lack of diversity within the field as one of the biggest threats to AI development going forward. And so we are trying to work with our team at AI for All towards trying to mitigate some of this and trying to bring in more people with diverse perspectives into the field. So we say that AI will change the world. It is already changing the world. And the question we ask is who will change AI? So our goal is to educate and support a diverse next generation of AI leaders, specifically thinking not just about the bottom of the pipeline, but really thinking about the decision makers at the top. So we've done a number of things, particularly most of our interventions right now are on the high school and early college level. So we've partnered with 16 universities to run summer programs for high school students from underrepresented groups. So this started at Stanford, spread to UC Berkeley, spread of course to Princeton, and is now at 16 other universities, including University of Michigan. We launched a free online open learning platform. So this is for the students that are not able to necessarily attend the summer programs, but to bring this to their classrooms and to themselves as well if they want to access themselves. Created college pathways. So this is for students from underrepresented groups who are in college already. And then honestly, perhaps the most important thing that we're doing is the alumni community. So we're providing lifelong training, mentorship, leadership opportunities, community events for our alumni. The ones that sort of choose to stay in this field, we would like to continue supporting them and continue providing opportunities for them. And my all-time favorite quote is from an AI for All 2016 student who said, "Until this program, I never thought that people who look like me could succeed in computer science and AI." And so this is why we do what we do. So I will conclude here, give a huge shout out to all of the students who've been involved in this work. So Kayu Yang, who is on the job market, is graduating with his PhD shortly, will be on the job market soon. Clint Nami, Jackie Yao, Angelina Wang, Dorothy Zhao, who's going to be applying to PhD program shortly. Seiyu Wang also will be on the faculty, the job market shortly. Yanis Karakoses, Vikram Ramswamy, and Sunny Kim. Very happy to take questions. Thank you.
Thank you so much, Olga. That was a fantastic talk. If anybody has questions, please use the Q&A link that you see at the bottom of your screen. So that was a very a nice tour through a range of topics that you covered there. Wanted to ask, in terms of understanding what's in an image for purposes of understanding bias. You alluded to different ways in which you would derive attributes from an image. A lot of that is from using, I assume, standard image recognition mechanisms and then looking at the text strings that you get. But you also talked about skin tone, which seems like a very custom attribute. And I guess my question is, are there image-derived, is there an ontology of image-derived attributes that matter, or how do you think about this?
Yeah, so I think what you're getting at, right, is like how much of this bias can be automatically revealed versus how much of this is like you really need somebody to either annotate the protected attributes for you, or at least sort of make decisions about what matters in the possible space of statistics that an automatic tool could reveal. So I think the short answer is, I think you kind of always need a person to make that determination, because so if we think back to like Revise, for example, the automatic tool, right, for revealing biases in a visual data set. So to Revise, at the end of the day, revealing something like, oh, computers occur frequently in offices is equivalent to revealing that computers occur frequently next to women rather than men. Like, to this tool, it's like the same kind of knows about a range of visual sort of structures, and it kind of says, okay, here's the correlations I've discovered, right? So, and then it is 100% part of what the people need to, the data set creators need to make. So this is part of why, like, we need diversity in the decision makers, because somebody's going to go ahead and make the decision about whether this is okay for the data set or not okay for the data set. And then might also depend on the, like, these decisions depend on how you generally think about like fairness or bias, but also how you think about what the goal of your data set is. So like, for example, in Revise, there's a number of analysis around like geographic diversity of your data set. But like, if you're trying to collect an autonomous driving data set in New York City, and the tool tells you, oh, hey, you know, all of your data comes from New York, it's like, yeah, I know that was the intended behavior of the data set. So I think there's a lot of like, both needing to make these decisions, but also like intent of the data set. And that's not going to be able to be automatable.
Thank you. There are a couple of questions in the Q&A box. Let me know if you can.
Yeah, let me, oh, great. There we go. I think like this, I can actually see it. Okay. Use face masking and, right. So right, but we need data to train these models for face masking and analyzing proportion for demographics, right? 100% right. Wouldn't this data have biases? Absolutely. And wouldn't this bias leak in through here? Absolutely. So, right. So I think there's a lot of questions about, so for example, if you are, so in the paper that I talked about with the analyzing racial bias in image captions, so one of the things that we tried to understand is, because we went ahead and annotated skin tone and gender for the people appearing in the images. So we actually got IRB approval to do this annotation because we needed IRB approval to get demographics of the annotators. And so those are self-reported demographics. So then we could analyze, you know, at least take a stab at like trying to analyze whether the demographics of the annotators affect their annotations. And it appears to be, for our case, because the annotations were quite simple, it appears to be that we didn't find an effect. So it seems like the level of agreement between annotators of the same demographic, coming from the same demographics and from different demographics, were the same in this case. But absolutely, so as much as possible, we can try to understand. I mean, there's bias everywhere in this pipeline. There's bias sort of everywhere in this cycle. So I think as much as we can, part of the research agenda is trying to like catch exactly where this bias comes from. The other thing that we can compare, right, is in some of the earlier papers we used automatically annotated gender versus like manual annotations of gender. And so we can again kind of compare how much bias that came from the fact that was automatically annotated versus manually annotated. But yeah, it's sort of always a moving target. You're always kind of playing this game of trying to make this as unbiased as possible, but yes, there's bias kind of coming at you from all directions. So I don't know that kind of, but yeah, the short answer is yes, you're 100% right there. And then, right, so the next question is, right, so you mentioned at the beginning, a bunch of the bias work done here operates on often inferred binarized gender in contrast to our modern understanding of the diverse nature of human gender expression and identity. How do we adapt these techniques to aid non-binary and trans folks who are often left to the footnote of debiasing work? So excellent question. So we are working on making a lot of these more diverse, more inclusive. So this is very much at the forefront of our minds. Some of our research work is looking at intersectionality, actually looking at sort of what gets lost when we're doing these fairness interventions specifically on one axis of identity. It turns out, so, I mean, in addition to just like, well, a lot of these interventions we need to adapt to sort of being able to have multiple protected attributes, but I think you also run into all kinds of issues with like insufficient samples. So which then makes it very difficult to both train as well as test your algorithms. In the intersectional setting in particular, you run into these like, from just a pure machine learning perspective, you run into these like very different amounts of diversity. And I don't even mean sort of social diversity, I mean like kind of statistical diversity within the groups, because you get into these settings where in a lot of modern data set, when you're looking at the race category, so there will be some kind of dominant races, and there will be a catch-all like other category. And so what happens when you have this catch-all other category with a lot of diversity in there, and then you intersected with 3 buckets for gender, which again, you know, 3 is obviously not enough, but even if you just say, okay, 2 is, you know, it's not just male or female, there is one more, and again, that's kind of becomes this like catch-all other category. Again, it has a lot of diversity within it. So, you know, I don't have any easy answers for you, to be honest. I hope in a couple of years to be able to give a talk that specifically sort of addresses these issues, but it's very difficult because you're sort of running, so a lot of the fairness concerns generally is that the models are making simplifying assumptions, and in making the simplifying assumptions are ignoring some sort of very important and socially important properties of the world, or amplifying sort of biases that create harm in the world. So now when you're trying to study fairness, you're actually kind of doing something similar where you have to make some kind of simplifying assumptions to then try to make the model slightly less biased. But then in making those simplifying assumptions, of course, that creates problems in and of itself. And so there's always, again, this kind of process of trying to make things better. And once you kind of have gotten a handle on the arguably like easier problem of fairness with respect to binary gender, right? So how can you extend it to the non-binary, to the trans community? Like how do you sort of proceed from there? And yeah, all of these are excellent and by and large open questions.
I guess that brings us to the end of a fascinating seminar. So thank you
And
very
thanks so
much.
much for having me.
It was really wonderful, and I think you've given people a lot to think about.
Thank you. Thanks very much.
Bye-bye.
Well, bye.